2017 Nissan Pathfinder. This is a direct injected engine, and on this video I'm just going to play around with the electric variable timing. It's only intake only, and what you see here is a three-phase brushless engine or motor, and it's all three phases here, and then this plug here contains a lot of the hall switches, powers, grounds, and I think even one of the wire monitors the temperature of the sensor. So I'm just going to manipulate this thing and play with it a little bit. I'm trying to learn how the system works a little better, and a little kind of peeling the onion back a little bit and getting in a little deeper than I think what the service information will tell me. So throughout the video I'm going to be doing some synchronizing, some cam and crank correlation, and then over here what I figured out through some experimentation is this is the control unit that controls the electric VVT, and you have two big wires, the pink and the red, that go into it, and then the black is the ground. That's the main power, or the current carrying wires, and they're fed from 250 amp fuses under here. So what I've done is I've figured out that the red wire that my amp clamps around is for bank 2, the one we're testing, and the pink wire is for bank 1. So the power is kind of split, so I'm able to see when the control unit is actually moving the motor and advancing the cam. And this control unit is kind of the muscle. The main ECU is here. It makes the decisions via CAN and then directs this controller here to kind of do all the heavy lifting, so to speak. It's quite a bit of current that runs through that, and I don't think the engineering wants the current to actually run through the ECM. It's just speculation. So anyways, I'm gonna have a bunch of captures. This is all known good, and just kind of like I said, just trying to figure out this system, get some known good under my belt, and before one comes in that's broke. So I hope you guys enjoy. So we'll start off looking at some pictures of some of the parts and pieces. This is the little three-phase motor. Your three-phase wiring's here. All your tattletale wires go in here. I don't have many captures of the wires going into this. I'm mainly looking at the effect of this motor on the cam crank correlation. It's kind of what I was after with this video. I did captures of it cranking, idling, snap throttle, and just tried to test the system a little bit to see what I'm looking for if this thing was sitting in my bay actually broken. But this little wheel, it basically spins. If it spins faster than the cam or the timing sprocket, then it advances. If it spins slower, then it has less advance. I don't think it ever spins backwards. It spins one way only. I just don't know which way that is. Most likely it would spin this way. But these little tabs here, they lock into this black area here. Spins free of the sprocket, and if you hold these in your hand, this turns very easily. It takes a lot of movement here to get very little movement out of the cam. It's like almost like a 4-low situation in a truck if you ever went off-roading. If any of these parts or pieces are replaced, there's like a learning procedure you have to do with a scan tool so it can find its stops and knows where it's at in its travels. Here's the picture of the back. This would be the exhaust, the sub chain, and this is the main chain, and this shiny piece here turns independently of the sprocket. So this is where your variable cam timing comes into play. So if it turns it one way, this is a stop. That could be maximum advanced, or that could be the home position. And then if it turns it the other way, obviously it's either the maximum advance or the home position. I don't know which way is which. And that's where the cam keys to this part. and it's a pretty cool system. I've got some ideas of how I would test it from doing this type of experimentation, or if the car was in my bay with a nose start, especially a crank nose start, and I start looking for cam and crank correlations. Some interesting things the system does that may throw you off, and you'll see all that as I go on. So this is all known good. This is pure experimentation on my part, and I just want to put a video together and kind of stick this information out there for anybody else who's got similar stuff or works for Nissan, and you may encounter these things. So enjoy the video, and we got lots of captures to go over. Alright, before we get going too much, I want to lay a little groundwork on what we've got going on here. So this capture is the car simply idling. It's in the bay. I haven't manipulated or doing anything to the vehicle. It has no codes, runs fine. This is simply just testing known goods and experimenting. So let's cut into a little bit here and talk about what we've got. This gold trace, that is an ignition sync. It just happens to be on number 2. The green trace is the crankshaft sensor. The red is the cam sensor. These are the two we're going to focus mainly on this whole video. And because I wanted a known good, this is the exhaust. So exhaust, intake, crank, ignition, all on bank 2, all known good. So if you want to take a screenshot of that, it's a 17 Pathfinder with the direct injected engine. You have two different engines you could get with this Pathfinder. One's a regular engine with oil controlled VVT and tune port injection. This is direct injection with electric VVT. I want to go over real quick. You're going to hear me talk about degrees and crankshaft movement. So I wanted to show you real quick how I figured that out. I'm going to turn the exhaust cam off. It'll probably be the last time you see it. So it's out of here. The falling edge, I call this the home position. You can see where it falls. See how it falls not quite in the center of the gap, but just to the left of center. I'm referring to that as the home position kind of throughout this whole video. So I want to figure out how many degrees of crank rotation are each one of these pulses or toggles worth. So let's start that process. So if I put a ruler here, on the falling edge of the ignition command is where the spark would happen. And so when number 2 fires again, and then when number 2 fires is 720 degrees. So let's make a quick measurement. We want channel C. I want to do a falling edge count, and I want to measure the falling edges between the rulers, and I'm going to hit OK. So between the rulers, I have 108 falling edges. That means if I divide that number in half, that'll tell me how many falling edges are in 360 degrees, which would be 54. And what do I mean by falling edge? What it's doing is it's counting, here's my first ruler, it's counting that falling edge and every one of them over to this one. So right there. So basically I'm splitting the toggle after the IC command in half, and I'm splitting the toggle after the IC command. So I'm basically measuring the same spot to give me an accurate measurement. So this measurement's kind of live. So what I want to do is I want to roll this thing into 54. Right about there. So now there are 54 toggles here. Now if that gap if you measure this gap out, 2 toggles can fit in each gap. So 54, 55, 56, 57, 58, 59, 60. So if those gaps weren't there, there would be 60 toggles in here. Well, 360 degrees divided by 60 equals 6. So each toggle is worth 6 degrees of crankshaft rotation. So that's how I'm figuring this out. So when you hear me talk about degrees of movement, it's based on this math. So because we're going to do idling, some snap throttles, some cranking. I've got a video where I've done some live stuff in the shop, and I'm actually using the scan tool to move the cam around. I'm unplugging it, and you're going to see all kinds of stuff, how this thing defaults. I think it's pretty neat. So bear with me as I work through it, and that's the groundwork, and we're going to build from there. Alright, so what I've done in this video, or this capture here, is basically I'm doing a clear flood mode. I'm just cranking. I hit the button, had to throttle to the floor, held my foot on the brake, and it cranked its entire allotted amount of time. So let's go over the signals. Start at the top. Now I've switched colors on you guys. The blue is the cam. The red is the crank. The gold here is battery voltage. I just wanted to include that so we can see when it starts cranking and then when it levels off. And then now the green, that's where my current clamp is. It's on that big red wire that we saw at the very beginning. That's controlling the VVT. And this is probably one of the more interesting captures. So let's just zoom in right here at the beginning. First off, if you want to do a real battery test, 858. This battery's a little low, but I've been cranking on it for a little while. You don't really need a VCAT to tell you you've got a bad battery. You guys know what I'm talking about if you know what I'm talking about. This is a real test. But here we go. So when this thing is cranking, so from the time it starts cranking till the first big current spike of it moving, trying to move things, is 350 milliseconds. So before any current hits, my cam is kind of in what I call the home position. I think it's laying against one of the stops that we saw when I showed you the parts. Alright, so we had a huge amount of current rush in, which is the very next toggle. And it's already moving that cam. So from the time it's cranking till the cam starts moving, we're still under 400 milliseconds. Well, if we go on, and then it hits it again, a lot of current. So basically it's spinning the center faster than the sprocket's turning. So then we move up to here. Now look how far it's already moved it. You're figuring there's 12 degrees plus in here. So this thing's moved this thing about 18 degrees in a little over a half a second. I think this is a startup strategy. And where this would be important is if you're doing cam crank correlation on a car that will not start. So now that the thing's kind of evened out, you can see it is holding this cam advanced. So why is it doing that? We're advancing the cam. So in theory, we're creating more overlap. Maybe we're getting more air in the engine. We're closing, if we're opening the valve early, that means we're closing it early, which we're raising compression, which generates heat. All of things to me that under normal circumstances you would want to do if you're trying to clear a flooded engine, or if you're trying to heat a converter up a little bit quicker than normal, you're going to help oxidize it. These are all things I'm speculating, but to me, the most important takeaway is this. If this car was in your bay, let's say it had a bad fuel pump, or for whatever reason this car's not starting, and you want to look at a cam crank correlation, this thing cranking compared to known good idling is not going to be a good comparison, because as we saw, idling, the falling edge is in home. Cranking, this thing's advanced, I'm going to say upwards of 15 degrees. If you're going to do this cranking, my suggestion would be to unplug the actuator, or unplug the giant plug that you saw in the video that's controlling these things, because this engine is advancing this cam while it's cranking. I thought that was kind of neat and worth talking about, because it's at home right there. I mean, the initial hit, it's at home. It rolls over again, it's starting to move it. I mean, this thing is moving this cam really quick. This is way faster than the oil control system, I believe, could do this. So probably why the car manufacturers are going to this system, but just want to put it all out there. I think that is very important. So I'm going to move on to the next capture, which I think is going to be a crank to start, and we'll check that out. Alright, so this capture is just simply crank to start, and then it idled. Everything's together, nothing's being manipulated. This is just the car, what it would be doing naturally. The black trace now is a math channel. It's kind of plotting our crankshaft signal. You can kind of see where you know, it's kind of down here at low RPMs when it's cranking, and then let me move that out of the way. And then it kind of flares up, got up to about 1700, and then finally it settled down about 740. I'm actually going to turn that off for a second, because it slows the computer way down with that on. So let's go back again to our cranking. There again, I've got the battery voltage there. She got down to 8.5 that time. So I think with this capture is the timing got a little aggressive, and then it realized it boo-booed, but the car started normally. So there's our home position, and you can see it's starting to ramp current up, because right in here the engine's actually cranking, and you can see how close the crankshaft signal gets in here. The engine starts running right in here. So it bumped a little current, and then it bumps it here. And then you can see we had movement. So it moved off of home. It moved our 12, 13 degrees advanced. Well, right in here, the engine starts. I mean, it's starting to run. And I think it bumped it again. It kind of maybe got a little aggressive with the movement, but then it calms itself down, and by the time the next spike comes in, we're back to our home position, because now the engine's idling. I thought that was kind of neat right in here, how it got the desired movement, and now that the cam pulley is spinning faster because the engine's actually running, the sprocket motor has to turn faster than the engine to keep that level of advance. And then as it backs off and the engine starts idling, it lowers the current and then lets this thing come back to the home position. In case you're wondering, this gap here, if I would have been monitoring the other cam sensor, it would have fallen in this gap. So bank 1 would have been there, there's bank 2, then back to bank 1, and back to bank 2. I'll turn my little RPM channel back on. Where's it at? You can see how it kind of ramps up pretty quick in engine speed. See, right in kind of right in this area, the engine's only running at, 210 RPM, so it's clearly cranking, but right, between these rulers within, 50 or 60 milliseconds, this thing jumps from 210 RPMs to 550, and then by the time it gets up into here, I mean, this thing is, working its way on up. It's up to 700 and some RPMs in that short amount of time. So I think it applied a lot of current and then had to back off of it a little bit because the engine started. I'm not implying that this cam has to advance for the engine to start. I'm simply stating that I think they're manipulating the cams to help the engine start and to maybe create a condition that, in conjunction with changing the way the fuel injection works, to help with catalyst warm-up. I kind of think that's what they're doing, but it's just good to know that they're really manipulating the cams, the intake cams, on startup. And this is a warm start. I don't think there's any difference with a cold start as far as the cams. I did not check it, but I have looked at scan tool data, cold start versus warm start, and it looks the same. But I have not scoped it, so I didn't have time to let this car cool completely off before I had to release it. But I may end up having to do a part 2 on that. So once the car starts, it gets over its initial cam movement and then gets on out here to where it's just idling. We're kind of back at our home position. So the next capture I'm going to go over is a snap throttle, and you'll really get to see a lot of movement on that. So hang on. All right, so this is a snap throttle. As you can imagine, where the current really ramps up is where we're really manipulating the intake cam. So right in here was idle. So let me just cut right in here. So we're kind of at our home position. These are the little current ramps. And I don't want to make you guys dizzy, but I'm just going to zoom kind of through here. Now, Nissan, they kind of delay a little bit. So when you push the APP, it's not immediate. It's no throttle cable. You guys know that. The APP gets pushed. It's an input. It has to be processed, and then the throttle opens. Well, I think some of that is the engine getting prepared for this big gulp of air that's getting ready to come into it. I don't think it's instantaneous, especially setting in a bay, trying to snap the throttle without it banging off the rev limiter or two. So pretty much, as you can just see, the things ramping up, and as it's starting to apply current, you can kind of see the cam's already moving. It's already moved 12 degrees by right there, and then we just keep kind of popping on over. You can see how close the crank sensor is getting. And it's really starting to move this thing. Let's see. So if each one of these is worth 6 degrees, so that's 6 by 4, so there's 24 degrees plus, the movement from here to here. So let's keep going. Right in here where it really gets dark. 1, 2, 3, 4, 5, 6, 7. So you're getting 40, 45, maybe pushing close to 50 degrees of movement out of these things. That's really getting a lot of overlap. Help these things breathe a little bit. And you get a lot of current movement in here. This thing's really bouncing the current because you figure the engine's turning faster, so this little motor has to turn faster, even, and more work requires more current. So it's definitely moving it right along. And then after it calms down, you know, the engine's kind of coming back down to normal. You can see it's starting to kind of work its way back home. And then out here I thought was kind of neat. Where's it at? I hate to keep doing it this way. There you go. So it's back home, and I mean, it's applying nothing. It is just like, I'm happy where it's at. So I think right here is kind of where these things are laying on a stop. Now I'm going to play you a little video. I had to record it live in the shop, and I'm using the scan tool to move the cam, which is kind of neat. I did another video on that a while back on electric VVT, but it's a totally different system. This uses, like I said, the 3-phase motor, brushless. The other video I did was it was a 2.5 Ultima, I believe, and it had a brushed electric VVT system. Worked very similar, but I think this is going to be a lot. I think this is going to be around longer. To me, this is a little tougher. We have been seeing a few problems with this system. I've read about a lot of problems, and you know, people are saying, well, I replaced this, I replaced that, I replaced this, but there's nothing being said. Why are you replacing it? That is my goal for trying to learn this, because let's say, for instance, I see this amount of current, but I don't see that cam move. Well, that kind of tells me something's stuck, right? You know, an electric motor, you know, it's kind of like when your wipers are iced to your windshield, you know, and you turn them on, you know, I'm thinking that wiper motor is going to pull a hell of a lot of current trying to move stuck wipers. I think this kind of testing and kind of knowing what to expect will help you diagnose this when the car's in your bay with some weird cam timing code. These engines there again are direct injected, so you know you're going to get increased timing chain wear, and you know our customers always change their oil on time, always, so that's going to help deteriorate slack in chains and things like that. And knowing that this system can move that cam 48 to 50 degrees, and let's say it has to compensate for 10 degrees of slack and can only move it 38 degrees, well, is that enough to trip a code? Service information, I've heard 13 degrees difference between what it wants and what it's getting. If it has to overcome a bunch of slack, that could be, you know, a code set. There's codes for these systems with over temperature, which there again, if you've got you know, some sort of a sticking sprocket that this little motor has to pull a lot of current to get it to move a little bit, you know, I think this style testing can help diagnose that before you just blindly tear the chains out of this car, which is a lot of work and a lot of expense and a lot of time just to blindly chunk parts in. At least if you've got some sort of a capture, you've got some direction, you know, okay, so this is doing this and this is why, so now I have a reason. I think I can justify pulling the timing cover off this thing and taking a snoop. So kind of the reason I'm putting all this out there. After I play you the next little live video, then you're gonna hear my little thanks for watching music. And if you want to stick around after that, I kind of back probed all three of the phases voltage wise and compared it with the current. I do not understand exactly what I'm seeing, but I did back probe it just to kind of take a peek at it. I might put up a couple of captures after that if you guys want to stick around and just check that out. It's more of an interest versus I wouldn't use the voltage, I don't think, as much for diagnosis. I'm going to kind of look at the current, but I'll put that up later. We'll call it a little bonus thing going on. But enjoy the video. I hope you guys learned something. I've learned a lot. I've actually learned that I have a few more questions about the system that I'm going to try to answer for myself, and if it's anything kind of cool or interesting, I may make a part 2. So thanks again for watching. Alright, so I've got a advanced trigger set up here on the blue trace, which is my intake cam. The yellow or the gold is the crank. The red is the ignition sync, and the green is the current that I showed you in the video. I'm on the the big red wire coming off the controller. And then over here to my left I have my scan tool, and I'm just going to advance the cam, and you'll see it move to the left, and then you'll see the current kind of spiking. And then it's kind of neat. I'm just going to do it kind of slow, and you can see the cam is moving to the left. Now if I click it kind of fast, you can watch how the thing spikes the current a lot. See, it's demanding it to move faster, and that's about the maximum I'm going to get. But you can see it moved over a tooth or so. Now what I'm going to do is I'm going to unplug the big 3 wires that are at the 3-phase motor, and then you'll watch it, it'll go back home. So I have a couple of theories about that. Now see how it went back home. See, right now electrically that motor can't even spin, so I'm guessing it's just along for the ride at this point. It can't advance or retard this cam at all. So my suggestion would be, if you're capturing known goods, to disconnect the system somehow so you can see the raw data. Let me plug it back up. I may have to cycle the key to get it to go again. So anyways, I think that's kind of neat. Yeah, the system's offline. It's probably got a couple of trouble codes in it, but kind of neat how it works. And just kind of get this thing figured out, because I don't want to be doing this if there's a car broken in my bay. Alright, so this is kind of like the little bonus area. There's a lot going on here, and most of it I don't know what it is. But I did the capture just because I may have to study it and learn more about it. But the green is still the current, and these other 3 here are basically the 3 phases. That's the voltage. I'm just back probing it. The engine's just idling. It would have been in the home position, and this is kind of what the voltage looks like. I'm thinking things happen every 120 degrees, because it's 3 phases. So, but like I said, these signals are pretty fast if you zoom way on in on them. I did have my sample rate set at 1 microsecond, I think. It probably wouldn't hurt to sped that up a little bit, because it looks like I'm kind of getting some rounding and stuff in here. But this was just mainly for curiosity. I wasn't looking to glean much diagnostic info from this. I was kind of worried about the current. So it looks like the current's ramped up when the red's really high. There, the gold's high. Like I said, I'm still getting into the 3-phase motors as far as what the electric looks like, but I'm pretty sure a lot of the stuff I went over with the current can be used. So that was idle. Here's the crank to start. Remember how it kind of advances the cam to start with that big ramp up right there when I was showing you the correlation. That's what it would look like on the voltage side. So there's a lot happening in here. I mean, you got a nice big spike there, because I don't think these things ground through the other phases. I'm not sure. But when you kind of zoomed, not really tight in, but I mean, that actually looks kind of cool. You can see the 3 distinct phases right there. So I'm wondering, just out of curiosity, if we go, let's see, how would I do this? If I went, if that's my starting to, would I go to the end point? Start to start. I mean, you can kind of see that's 120 degrees, that's 240. I don't know, guys, just thinking out loud here. But anyway, that's the crank to start to idle. And then I have one here with the snap. Snap throttle right there. This thing really goes nutso on me here. A lot happening, just a lot to take in right there. Got these kind of these big pulses here. Yep. And out here it just calms back down and gets back into what I call normal. I mean, that looks kind of uniform. Let's see something here. 360. So that's kind of cool. You got 0 degrees, and then 120 degrees later you have the start of the gold one, and then 120 degrees you have the start of the blue one. I don't know, it's the only kind of the place it lined up like that, but just throwing this out there, topic for conversation. If you guys stuck with me this long, I certainly appreciate it. Thanks to everybody who's using the Autonerdz link. I haven't talked to Trevor in a while. I don't know what the availability of scopes are right now, but if it's something you got to have, tax season, if you're getting a bunch of money back, now's the time to invest in a scope. Give old Trevor and Brian and those fellows over at Autonerdz a shout out. They help support my channel, so I definitely got to support them and the Pico group and all the things that are offered if you do purchase from them. So you guys have a good one, and I will see you on the next video.